In this video, I want to show how to do differentiation and integration in polar coordinates. So we'll start with differentiation. And just so you know, we're still going to be doing stuff like dy over dx, except we'll be dealing with y being r sine of theta and x being r cosine of theta. So let's start with a simple one. Calculate the slope of the tangent line to r equals 3 when theta equals pi over 4. Hopefully you'll remember that this is a circle of radius 3. And let's take a look at what is involved in taking this derivative. Well, as we before, we know that x is r cosine of theta, and r is the constant 3 here, so I'll get 3 cosine of theta. Then dx over d theta is equal to negative 3 sine of theta. Similarly, y equals r sine of theta, and that's equal to 3 sine of theta. So dy over d theta equals 3 cosine of theta. And then just like with parametric equations or parametric formulas, dy over dx equals dy over d theta divided by dx over d theta. And I already have the dy over d theta, so that's 3 cosine of theta. And then the dx over d theta is negative 3 sine of theta. The 3's cancel out, and you end up with negative cotangent of theta. Well, we wanted this when theta was pi over 4. So dy over dx when theta equals pi over 4 equals negative cotangent of pi over 4, which equals negative 1. Now, I urge you to use your calculator to help you check these. Let me show you what I'm talking about. Bring up your calculator, make sure that you first of all are in polar coordinates. Let me check my mode. I'm in POL, that is polar. So I'll go to y. Let me clear this and clear this next thing. R1 is simply equal to 3. And then we know that this is a circle centered at the origin of radius 3. But what I'm going to do is make sure my window can see it. And I'm going to give myself a little buffer room. Let's go negative 5 to 5 on the x's and negative 5 to 5 on the y's. And 0 to 2 pi is fine because that will be a complete period. And no surprise there. This is your calculator's version of a circle when it's not been squared. Press zoom 5 and we'll get a more circular circle. Now I do want to check though the value of the derivative when theta equals pi over 4. Pi over 4 is right smack dab in the middle of the first quadrant. So here's how I do it. If I go to my window settings and I change my theta step, you can really pick whatever you want here. If I go 0.1, it will go every 0.1. If I go 0.01, it'll go every 0.01. But that's very slow. What I'm really interested in is finding out if what I did at pi over 4 is the right thing. So if I can't just, here's what you can do. You can do something like this. 0.1 1. Now this may seem strange, but times, and then I'm going to go second pi divided by 4. Then down arrow it. It does a decimal version of what you just did. All right, let me go ahead and graph it again. I'm not going to touch anything, but I want you to see how slow. It's slower now. We see how it started at theta equals 0 and went around till we got to theta equals 2 pi. Now go into the calc menu. That's above the trace button. Second trace. And look what I have here. dy over dx is my second choice. Now, since I chose 0.1 of pi over 4, if I move this exactly 10 spots, there's 4, 5, 6, 7, 8, 9, 10. This is pi over 4. When I hit enter, it will tell me the value. You see that dy over dx is -1, which agrees with what I just did. So this is a beautiful way to be able to check your answers, at least for differentiation. Integration, there are ways, but it's not so straightforward as this. Example 2. R equals 3 can also be written as x squared plus y squared equals 3 squared. What I'm going to do is I'm going to redo the first problem, but I'm going to do it in classical Cartesian coordinates to show you we get the same answer. When you're trying to find dy over dx in a situation like this, you typically take the derivative of everything with respect to x, something called implicit differentiation. When I differentiate, the x part becomes 2x as normal, but the y part's a little bit different. You have to use the chain rule. I'll get 2y to the first, so I get 2y, but then you have to multiply by the derivative of y, so I'll have to multiply by y prime. The 9 part is 0 after you differentiate it. I'll divide everything by 2, and then solve for y prime. And of course, we did have negative cosine over sine. That shouldn't be any surprise to you. But now, I don't have an angle to work from, but at theta equals pi over 4, x was equal to, what was that, a circle radius 3. So x is equal to 3 radical 2, and y was also equal to 3 radical 2. So I'll plug those in, and I'll get negative 3 radical 2 divided by 3 radical 2, which will equal -1, just like we had before. Let's compute the slope of the tangent line to r equals 4 plus sine of theta at theta equals 3 pi over 2. Well, I'll use the same formula as I did before. X equals r cosine of theta. However, the r that's being put in here now is more complicated. I'm going to have 4 plus sine of theta times cosine of theta. So then when I take this derivative, dx over d theta, I'm going to use the chain rule. This will be my first function, the stuff in parentheses, and the cosine theta will be my second function. So taking the derivative of 4 plus sine of theta ends up giving us cosine of theta times cosine of theta. And now, leaving the first of the functions alone, I'll end up with 4 plus sine of theta times negative sine of theta. I honestly don't care much about simplifying here. We're just going to be plugging in a number, so it's not that big of a deal. I will rewrite it just a little bit. Cosine squared of theta minus 4 plus sine of theta times sine of theta. And for anyone thinking like, oh wait, cosine squared and sine squared gives you 1, there's a minus there, not a plus. Similarly, y equals r sine of theta. That equals 4 plus sine of theta times sine of theta. And I'll opt to do the product rule again for this derivative. So dy over d theta equals 4 plus, the derivative of 4 plus sine of theta is cosine of theta, plus 4 plus sine of theta times cosine of theta. So I'm sure you can do a little simplifying. Like I could factor out a cosine of theta and end up with, if I simplify it and I think it'll do something useful for me, I will do it. If I do that, I'll have 4 plus 2 sine of theta. And so now we're on to the derivative. dy over dx equals dy over d theta divided by dx over d theta. The dy over d theta gives us cosine of theta times 4 plus 2 sine of theta over, and for the other one I have cosine squared of theta minus 4 plus sine of theta times sine of theta. So now I'm ready to plug in 3 pi over 2. So that would look like this. dy over dx evaluated at theta equals 3 pi over 2 equals, and like you figure, I'm just going to plug in 3 pi over 2 wherever I see a theta. So I get cosine of 3 pi over 2 times 4 plus 2 sine of 3 pi over 2. All of this stuff will be divided by cosine squared of 3 pi over 2 minus 4 plus sine of 3 pi over 2 times sine of 3 pi over 2. Let me go ahead and evaluate all of these numbers. Cosine of 3 pi over 2 is 0. So it might lead you to believe that the slope is 0. However, if the denominator turns out to be 0 also, we're in trouble. So let me put what I've got for the numerator here. I've got 0 times 4 plus 2 times 1. Sine of 3 pi over 2 is actually negative 1. Cosine of 3 pi over 2 is 0, so that's like 0 squared there. Then I have minus 4 minus 1 times negative 1. I don't really care what happened in the denominator now because it's not 0. So what I get for the whole answer then is 0. That means that the tangent line is horizontal at that particular spot. And I urge you, let's graph it and see what actually happens. So the function to be graphed is r equals 4 plus sine of theta. So I'm going to throw that into the calculator. I'm going to clear out my y and replace it with 4 plus sine of theta. I think what I'm going to do, I've not tried it before. I'm going to try it now. I'm going to do zoom. Instead of 6 for my zoom standard, I think I'm going to do zoom square and see what happens. Let's just see what it looks like. Oh, that's a nice looking circle. Look at that. I'm interested in it 3 pi over 2. So if you go back to the window, I can play the same game I did before. My theta step, I can do 0.1 times 3 pi divided by 2, and it lets you do that. That way, when I come back to the graph, it was pretty fast. I don't really care what the graph looks like. I just want to get to down here, where we're at 3 pi over 2, and then I'm going to calculate the derivative at that. So I'm going to go up to Calc, choose dy over dx, enter, And now let's go exactly 10 marks, and I'll get there. I think it's at 10. I'll keep track of the theta as it goes around. Right there. This 4.71 is 3 pi over 2 as far as the calculator is concerned. You can see the x, if it had more decimal places somewhere buried in memory, maybe this would have been a 0 if it could do it. But it is a 0, as TI will tell you. The y, of course, is -3. Let's hit enter. And what do we have? dy over dx equals -3.85 e -10. That means that there are precisely 9 zeros before the 3. That would be a very close to 0 number, so it indicates to me that 0 is the right answer. So this has been checked. Let's compute the slopes, there'll be more than one here, of the tangent lines at the tips of the leaves to r equals 2 sine of 3 theta, y equals, and in this case I'm going to clear this out, we have 2 sine 3 theta. Remember, this means that when you put a 3 here, the period of this particular function is now 2 pi over 3. I am going to do zoom 5. I find that more interesting. I don't see a thing. Well, what that means is you should probably zoom in. Let me change my window to something more aggressive. I'll stick with 0, 2 pi because that feels comfortable. The theta step, I'm going to go to 0.1. That's kind of my go-to if I want a quick graph but with enough detail that I can see what's going on. X-min, I'm going to decrease my dimensions to -3 to 3. This is just a guess. I'm not actually, I haven't computed anything in my mind. I'm just guessing. This is going to be closer than what we had before. There we go. So you can see what it did. Let me go back. I'm going to change the theta step to 0.01 so you can see how it's drawn. It's important that you know that. Watch the graph. See, it starts when r is 0, comes around. This is when r, I don't know what it is, but r is 0 here, comes around, then r is 0 again, comes around, and finally ends there. Now stop for a minute. Do you see this? This indicates to me that it's still calculating stuff. That little symbol up there is still actually doing stuff. That means 0 to 2 pi was more than was necessary. I wonder if I could change it to something less. How about 0 to pi? And let's graph it again. So there we go. Here we go. Now, if I'm right, this busy signal will disappear when it gets back to the beginning. There, did you see that? It did disappear. Now let's take a picture of this. Now, I don't think I need the greatest graphical display to get the idea to you. We saw the way it was graphed. It started when theta was 0, and when theta is 0, sine is 0, so r is 0. So it starts actually at the origin. And as theta increased, you saw how it was graphed. It graphed out and out and out and out and out, and it came back into another place where r was 0. And then if you watched it, it went through the origin, went down, third, then the fourth quadrant, then it came back up and shot into the second quadrant and came back. It's important that you see how that went. It crossed the origin several times, and all of those are where sine of theta was equal to 0. So if we want to find out how many times it actually crossed through, or when it did that, let's set this 2 sine of 3 theta equal to 0. Well, the 2 is meaningless, so I'll just go sine 3 theta equals 0. Now, you don't have to recall every place. I don't have to come up with a formula for where sine is 0, but you know that if the sine of a function is 0, I mean the sine of something is 0, then that something has to be a multiple of pi. So you know that 3 theta is going to equal something. It'll be either 0, pi, 2 pi, 3 pi. The list goes on and on and on. I don't really care. I'm just interested. Actually, this happened all within one pi, so I'm not going to bother with anything more than what I need. I'm going to divide by 3, and I'll get theta equals 0 and pi over 3. I don't care about the rest of it. But I'll put it here for reference so that you can see what happened. When theta was equal to 0, we were at the origin. So there's a point. Now, by the time it got to pi over 3, that means it went around and did this leaf of the rows. And it got back there at pi over 3. So you can take these, the beauty of these things is they are so symmetric about lines in the middle. For example, if I draw a line directly in the middle of this leaf, headed towards the end of it, the point I'm making is if I cut right through the heart of that leaf, the angle from the positive x-axis to that ray that I just drew is half of 0 to pi over 3. That means it happens at pi over 6. So what I'm trying to say is if I want the slope of the tangent line here, so I'm trying to get the slope of a tangent line there. What is the m for that? So I want the slope of that line. That means I'll calculate the derivative at theta equals pi over 6. So let's have x equals r cosine of theta, and the r will replace with the 2 sine of theta. 2 sine of 3 theta times cosine of theta. I'm going to use the product rule to get dx over d theta equals the derivative of sine, of course, is cosine, but when you have a 3 theta, you're going to get cosine of 3 theta times 3. All in all, you'll end up with 6 cosine of 3 theta times cosine of theta. And then when I take, leave this piece alone, but when I take the derivative of cosine, I'll get a sine of theta and a minus sine. So I get minus 2 sine of 3 theta times a sine of theta. Don't try to combine these things, they're not compatible. Y equals r sine of theta, which equals 2 sine of 3 theta times sine of theta. Product rule will give me this derivative also, dy over d theta equals, same deal as before, I'm going to get 6 cosine of 3 theta for the first part. Second part, I will not pick up a minus sign, but I'll pick up a cosine of theta, so I get plus 2 sine of 3 theta times cosine of theta. And now if I want to do the derivative, evaluated at theta equals pi over 6, I'll simply replace theta with pi over 6. So the numerator part is the dy portion. I'll get 6 cosine, 3 times pi over 6 will be pi over 2 times a sine of pi over 6 plus 2 sine, same deal as before, pi over 2 times cosine of pi over 6. All of that will be divided by this expression for dx over d theta. I'll get exactly, this will be the same thing there. I'll get 6 cosine of pi over 2 times, but then I'll have cosine of pi over 6 minus 2 sine of pi over 2 times sine of pi over 6. Now these aren't as bad as they look. A lot of things do zero out. For instance, the cosine of pi over 2's go away. That's a 0. This one down here is 0, so I can get rid of those things. What I have left then, I'll have 2 sine of pi over 2 times cosine of pi over 6. Sine of pi over 2 is 1, so I'll get 2. Cosine of pi over 6 is radical 3 over 2. All of that will be divided down here. I'll have negative 2 times 1/2. And all this, after all is said and done, I'll end up with negative the square root of 3. And that should make sense from some aspect. This is most definitely a negative slope. The fact that it's negative radical 3, you can check on your calculator like I did before. All you have to do is use your calculator to tell you that this is roughly 1.732. And that's where you'll be looking. However, I want you to see something else. Let me grab this picture and bring it down. If I wanted the derivative at all of the leaves, it's very simple now. I know that at this point here, my m equaled negative radical 3. Well, using symmetry, this other leaf is like a mirror. That means at this place, which will be, if this was at pi over 6, this is pi over 6 measured from the x-axis. That's 5 pi over 6 if you measured from the positive x-axis. Well, in any case, using this as my guide, the m here equals radical 3. I didn't have to calculate anything to get that. Next, the end of this leaf here, this is pretty obvious. The m equals 0. So there we have, just by doing one of them, I'm able to get the slope of the tangent lines to all of the edges of the leaves. And where did they even occur? Well, there's one right there. That occurred at pi over 6. Let me draw another one that would have stopped here in the middle of that one. That was 5 pi over 6. And if you want, they're going by 4 pi over 6 thereafter. This here, by the time I get to the third one, let's go in here if I can. Halfway is pi over 6, 5 pi over 6. This would be 9 pi over 6, or if we simplified, 3 pi over 2. Symmetry is so evident in all of these problems that you can save yourself at least 50% of the work by making use of it. Obviously, the next topic is integration. And before I begin that topic, let's start with a circle. And you know that the radius is r. And let's say I have a wedge in it whose angle is theta measured from the center. The area of that sector is, well, you can sort of guess it by taking a look at an entire circle. That would have an angle starting from 0, would measure all the way around an angle of 2 pi. But we know that the area of a circle is pi r squared. Or if I rewrite it, that's r squared times 2 pi. And let me, in front of the r squared, let me put a 1/2. This seems like a strange thing to do, but when you see what I write next, you'll understand. The entire circle to go all the way around is a theta of 2 pi. That was 1/2 r squared theta. So the area of this sector right here is exactly that. So what we're going to do is use this as our basic unit of measurement, if you will. Just like when we did calculus, the beginning integration, we used rectangles as our basic unit of area measurement. So our basic unit of area is the sector. So now, if I have some sort of a strange area, and in time you'll grow comfortable with these regions and knowing what to use when, but let's just say I have some sort of a weird shape, like so, but it emanates from the origin. So let's say I want to find the area of this creature here. And let's say I have a beginning angle measurement of alpha, and let's say I have an ending measurement of beta. So I'm going from alpha to beta. How do we compute this area? Well, the way we do it, I think I want a bigger picture, for one thing. Beta is like a bee with a long tail. What we do is, like we always do, we partition the angle up, or the span of the angles up, something like this. And it goes on and on and on. My drawing is getting worse and worse as I go on. But what I want to do, though, is make sure that the angle between successive arcs, if not arcs, but successive radii, is always going to be the same. So I'm going to call those delta theta. That'll be, all of them will have that angle in there. So just like we did delta x, we wanted the same. Life will be easier if we just use a delta theta. Now what we do have, we have a starting radius here. Let's call it r sub 0. And then we'll have an ending radius that we'll call r sub n. Hopefully you can see what's going on here. Then what we do, from r sub 0, we'll draw a circular arc that will be the same, that will be a circle whose radius is r0. Then from the next point, we'll draw a circular arc whose radius is r2. From the next point, we'll do another arc. Notice these won't be exact because the next arc is not at the same level, so I'll move this so it has the same r at the end as at the beginning of that subinterval. But what we're getting then is the following. We have, each of these have an angle inside of them of delta theta, and each of these is the length of an r. In fact, I think it's better if I make this an r1, because I want this piece and this piece to be r1, and then I need the next piece to be r2, then r3, and it goes on. So what is the area of all those things? So the area is roughly the sum from k equals 1 to n. What was our formula? Formula 1/2 rk squared delta theta. But you know that as n goes to infinity, all of these little circular arcs will start to conform to the curve exactly, because delta theta will be going to 0. So as n goes to infinity, you will have a will equal the limit as n goes to infinity, sum k equals 1 to n, 1/2 r sub k squared delta theta. Now keep in mind, these don't have to be equally thetas. It's just going to be the easiest for us to calculate. So in some books when you read, you may see a delta theta sub k because they are taking into account that these individual angles could be different. But you've seen this before. This here is a Riemann sum. This is a limit of Riemann sums. We know this to be the integral. where did the integral start? It started at an angle of alpha and ended at an angle of beta. Alpha to beta. The 1/2 I'll pull out front. R sub k becomes r. Delta theta becomes d theta. Let me sneak a thing around here. And this is the formula that we will be using. It's important for you to know, though, that the movement is counterclockwise. If you go clockwise, you'll get the negative of your answers, just like if we switch direction with regular integration. So let's do some examples to illustrate what's going on. Now, you should know r is usually given as r equals some function of theta. So most of the things you'll see won't actually put an r here, but they will actually put the following. 1/2 the integral from alpha to beta. Notice alpha and beta are the Greek versions of a and b. Instead of r, we'll have f squared of theta, d theta. So this is the version you'll most likely cover in a book, but I'm not really sure this f. Some students just look at the formulas and write them down, and you'll miss the fact that it is the radius. The radius does change as theta goes from its beginning to its end. Let's compute the area of the left lobe. R equals the square root of cosine of 2 theta. Here, I think you're going to find that your calculator is going to be invaluable. It's going to be very important to get a picture of what's going on. Let's throw this in and then see what we're talking about. What left lobe will become evident after we look at the picture. So let me clear what's in there and replace it with the square root of cosine to theta and the parenthesis. And let me do zoom 5 just to see what my picture's like. If I don't see much, I'll change things. I also have it at 0.01. Let me come back to the window. I do want to draw it faster than I did. And I just noticed that I only went from 0 to pi, so I'm going to change that back to 2 pi. Now let's take a look at a picture again. Okay, so I get some sort of like an infinity symbol. I'm going to zoom in. So I'm going to change my window. It looks like I might be able to go from negative 2 to 2 in all directions will give me a much better picture. So I'm going to do negative 2 x min to 2. And then for y min the same thing, negative 2, y max at 2. Let's take a look at this graph. There we go. Now, due to the limitations of your calculator, you should know that it did intend to connect these. But the area of the left lobe then is this piece here. That's what I'm looking for. I want to go back to the graph. This is important to see how the graph is drawn. I'm going to go back to my window, and now I'm going to change. I think I should quit this. Go back to the window. What I'm going to do is change the 0.1 to 0.01. It will draw things slower. Now look, it starts here and ends here. So I'm going to, if you hit the on button, you'll stop. What we're going to do then is we're actually going to calculate this top half. We start here, and we go around. You saw the graph yourself. It ends here in the origin. So let me find out where this thing is, where r is equal to 0, and it will tell me this point. It started when theta was 0. You can check for yourself. Cosine of 0 is equal to 1. So this was 1. Anyways, let me find out where it hits the origin. So I'm going to set r equal to 0. Well, it's pretty easy to solve. Square both sides. Cosine of 2 theta is equal to 0. Well, where is cosine equal to 0? Cosine is equal to 0 at all the odd multiples of pi over 2. So 2 theta is equal to pi over 2, 3 pi over 2, 5 pi over 2, etc. I don't really care about all those. This to me is the very first time it happens. So I really care about just the pi over 2. If I divide by 2, I'll get theta equals pi over 4, 3 pi over 4, 5 pi over 4, etc. But what that tells me then is for my particular graph, it started here, make sure it's reasonable, yeah, that's reasonable, and ended here. Theta equals 0, and then when it got to the end, theta equals pi over 4. The r, of course, is equal to the square root of 2 theta. So let's throw this in. If I want the area of this thing, which is half of the answer, so if I want my answer, whatever I find for this piece, I multiply by 2. So the area I want is actually 2 times the area of this piece then, is the 1/2 the integral from 0 to pi over 4 r squared d theta. Well, this is nice because there was a square root in the thing. Here, if you square that, it takes the square root away. It makes it completely a joy to integrate now. The 2 and the 1/2 cancel. 0 to pi over 4 cosine of 2 theta d theta. And of course that equals 1/2 sine of 2 theta. And we're going from 0 to pi over 4. It's nice when you get sine many times, because if you start at a 0, sine of 0 is 0. I don't even have to use that in my calculations. All I have to do is plug in the pi over 4. So I get sine 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1, and we get an area of 1/2. Remember, we took care of the fact that we multiplied by 2 at the beginning. So this chunk here is actually of area 1/4, but it and the one below it comes up with the 1/2. Determine the area of the cardioid r equals 4 plus 4 sine of theta. So before I do anything, you actually don't have to see a picture. If I want the whole cardioid, I don't have a number in front of theta. All I really have to do is integrate from 0 to 2 pi. And that's r squared, so I'll have 4 plus 4 sine of theta squared d theta. If you don't mind, I'm going to take a 4 squared out. So I'll have 8 times the integral from 0 to 2 pi. 1 plus sine of theta squared d theta. That equals 8. Integral from 0 to 2 pi. When you square this, you of course have to use the FOIL method, and you get 1 plus 2 sine of theta plus sine squared theta d theta. And the way we handle sine squared is the use the formula involving cosine of 2 theta. I'll get 8, the integral from 0 to 2 pi, 1 plus 2 sine of theta plus 1 minus cosine of 2 theta over 2. Well, before I integrate, I'm going to do a little simplifying in here. I have 1/2 minus cosine of 2 theta over 2. I'm going to add the 1/2 to the 1, and I'll end up with 8 times the integral from 0 to 2 pi. I'll get 3/2 plus 2 sine of theta minus 1/2 cosine of 2 theta, d theta. Then when I integrate, I'm going to get 8 times 3/2 theta. These are the best. You just plug in the top and bottom then for those. Minus 2 cosine of theta. And then over here, when I integrate cosine of 2 theta, I'm going to get sine of 2 theta over 2. So I'll end up with minus 1/4 sine of 2 theta. And that's going from 0 to 2 pi. This is what I was talking about. 2 pi will affect cosine, but neither 0 nor 2 pi will have any effect on the sines. So no matter what you put in there, that piece is going to disappear. I don't even have to include it in the calculations. But for the rest, I'll get 8 times 3/2 times 2 pi minus 2 cosine of 2 pi. This part was 0, so I don't care about that. Minus 8. Here I'll get 3/2 times 0 minus 2 cosine of 0. The 2 and the 2's cancel here. I'll be left with just a 3 pi. Cosine of 2 pi is 1. I'll have minus 2 for that part. Minus 8 times 0. I'll have minus 2 there as well. And what will that give me? I'll get 8 times 3 pi. I'll get 24 pi minus 16, but then I'll get a plus 16. It looks like I will get 24 pi. Compute the area inside one leaf of r equals 3 sine of 2 theta. We graphed this one earlier, and inside one leaf, remember we had 3 identical leaves, and they went something like this. Well, if I want the area inside one leaf, I simply need to know where r is equal to 0 for the first and second times. R equals 0 when theta equals 0, so all I really need is when is it 0 again. So I set 3 sine of 2 theta equal to 0, or sine of 2 theta equals 0. Where is sine equal to 0? Well, they're multiples of pi, so you know that 2 theta must be 0, pi, 2 pi, 3 pi, etc. But all I care about is the first two, when it initially starts and when and the first time after that. So when I divide by 2, I'll get 0 to pi over 2. That will give me the area inside one leaf. So if I want the area, I'll have 1/2. The integral will start at 0, end at pi over 2. R squared will be this thing squared. 3 sine 2 theta squared d theta. 3 squared is 9, so I get 9/2. The integral from 0 to pi over 2 sine squared 2 theta d theta. Of course, I have to use that formula involving cosine of 2 theta for sine squared. So I get 9/2. The integral from 0 to pi over 2, 1 minus cosine of 2 times whatever the angle was. So I'll get cosine of 4 theta divided by 2. I'm going to bring this 2 out front, or 1/2, I guess. 9/4 integral from 0 to pi over 2. 1 minus cosine of 4 theta d theta. So that'll give me 9/4. The antiderivative of 1 is theta, because we're dealing with theta as the variable. And then for the second piece, I'll get 1/4 sine of 4 theta. And that goes from 0 to pi over 2. Notice again, the same thing happens as before. Sine of pi over 2 and sine of 0 are both 0, so it's not even going to figure in our calculations. Instead, I'll just have the theta part to deal with. So I'll get 9/4 theta is pi over 2. And then when theta is 0, I didn't even need to write that part. But my total answer then is 9 pi over 8. Compute the area of the inner loop of r equals cosine of theta minus 1/2. Inner loop. Well, what do we have? Let me graph that and see what they're talking about. It'll become evident once you see the picture. Let me clear this out. I'm going to change it to cosine of theta minus 1/2. Make sure you put your end parentheses before you do the minus 1/2 or you'll confuse your calculator. I guess I'll do zoom 5 just to see what kind of a picture we're dealing with, and then I'll wait, let me stop it. Go back to the window. Interesting picture. I'm going to zoom in, and let's go 2. Whatever, zoom in. There you go. You can see the inner loop a little better there. So I'll zoom out. All right, well, I'll change my window. Now I'll go from, I don't know, -1 to 2 for the x's. For the y's, maybe -2 to 2. Let's see if I've grabbed it there. Yeah, it looks like I got it. Okay, let me go ahead and take a picture of that. Remember to slow your calculator down, but it started at the end. It started here and then worked its way around, and then it went like this. Now, we want the area inside of here. And to make life easier for yourself, I think it'll be easiest to just find, well, I guess it doesn't matter. Find it when it starts and when it ends the origin. So let's find out when r is equal to 0. I want the first time r is equal to 0, and then as it goes around, I want the second time r is equal to 0. So let's take a look then. We're going to set cosine of theta minus 1/2 equal to 0, or cosine of theta equals 1/2. Where is cosine of theta equal to 1/2? Well, that happens at the pi over 3 locations. For example, pi over 3 in the first quadrant will do it. In the second and third quadrants, cosine is negative, so it's not going to happen there. It will happen in the fourth quadrant when you get to 5 pi over 3. So when it enters, as you go in that direction, theta equals pi over 3. And then when you exit again, so that comes in and starts going around, and then when you exit, that was theta equals 5 pi over 3. So if I want the area, I can do 1/2 the integral from pi over 3 to 5 pi over 3 cosine theta minus 1/2 squared. I'll FOIL it out and see what happens. Pi over 3 to 5 pi over 3 cosine squared theta minus cosine of theta plus 1/4 d theta. I'll use the double angle formula to reduce the cosine of 2 theta, cosine squared theta. And that will become 1 plus cosine of 2 theta divided by 2. Then we have minus cosine of theta plus 1/4. Before I go any further, I'm going to simplify a little bit. If I break this fraction up into 1/2 plus cosine of 2 theta over 2, I'll be able to take the 1/2 and add it to the 1/4. So I'll get 1/2 the integral from pi over 3 to 5 pi over 3. So 1/2 plus 1/4 gives me 3/4. Then I'll have 1/2 cosine of 2 theta and minus cosine of theta d theta. And several steps to go, but I will leave you with the answer. Pi over 4 minus 3 radical 3 over 8. I promise you there's nothing difficult about what you're going to be doing there. Compute the area inside of the rows r equals 4 cosine of 2 theta and outside of the circle r equals 2. Let's graph these two things together in one screen. Let's see what we're talking about. And I don't know what the window is. Let me just take a look at the graph real quick. Yeah, definitely I need more room, so let me change my window. I figure I'd probably at least go -4 to 4 in all directions. This is a row, so it's not going to go any more than -4 to 4 in all directions. So to give myself a little buffer, maybe I'll go -5 to 5. So I'll be able to see everything. Same with the y's, -5 to 5. And I saw it graphed very quick, but let me see if I can catch it. There's my rows, 4 petals, and there's the circle. Okay, that'll work. So we want the region inside the rows and outside the circle. That's talking about this region here. That's inside the rows but outside the circle. This region here. This region here. And then this region here. Your best bet is this. Even though your calculator does not make it look like it, but I think if I square it up, it might. If I do zoom and then I do, sometimes I hit something I shouldn't. Let me try zoom, and then I'm going to do 5, and you'll see they do look more symmetric. And the circle, of course, is more circular looking. What that means is, why don't I just calculate the area of just one of these partial petals here. I want to calculate the area of just one, and then what I'll do is I'll multiply my answer by 8, because there's 2, 4, 6, and 8 of those partial ones. let me concentrate just on that one partial petal. We had a circle of radius 2 come in and do its thing, and then the petal itself intersected that somewhere here. I don't know exactly what the angle is, but I intend to find out that angle for which that intersection occurs. And I'm going to drop my pictures because they're not doing it justice. So, where does the circle intersect the rows? And where's the first place that it happens? Because they both started their graphs at positive x-axis. So what that means is I started here, got to there, and for the circle the same thing. It started at 0 and got to there. Where's the first place that they intersect each other? So let me set them equal to each other and find out. I'll have 4 times cosine of 2 theta equal to 2. Divide by 4, and this looks like a similar problem to the previous. Where is cosine equal to 1/2? Well, those are at the pi over 3's. So 2 theta must equal pi over 3, and then 5 pi over 3. I'll divide by theta, pi over 6 to 5 pi over 6. I only care about the first time, so I don't need that. Just the pi over 6. So this theta, where they intersect, is at pi over 6. Let me put it out here so it's easier to see. That's the angle for which that happens. I don't know if you can see, but that's supposed to be a 6. So what we can do is, if I just do the rows, so the rows from 0 to pi over 6, of course these are theta values, this is what will happen. The rows will be drawn until you get to theta equals pi over 6, and then it will be intersected or stopped by a flat line. So this is what the rows will give me from 0 to pi over 6. Now, I didn't want all of that. I just wanted this little piece out here, the tip of it, if you will. How do I get that little tip? Well, what we can do is we can subtract from it the circle of radius 2 as it went from 0 to pi over 6. Let me draw better. Yeah, that's fine. That is the circle, and there's the pi over 6. So we could subtract off that little wedge of circle from this piece. Just so you don't have to memorize any formulas, this part right here is 1/2 the integral from 0 to pi over 6. R in this case was what? 4 cosine of 2 theta. So I have 4 cosine of 2 theta squared d theta minus, then this little wedge, this little circle, if you will. You can memorize, use the formula, or you can simply do this, 0 to pi over 6, and note that r is equal to 2, so you have 2 squared d theta. When all is said and done, you will end up with, now when I find this piece, remember, that piece was 1/8 of the whole thing. So if you wanted to get the exact answer, remember to do 8 times this whole quantity. And when all is said and done, you'll get 8 pi over 3 plus 4 radical 3.